Okay, hey guys, this is part 2 for problem 3. Part 1 was just showing you how to draw moment and shear diagrams in general, and I'll be posting several of those videos throughout the semester for you. This is how you actually, so the last part was drawing moment and shear diagrams. This is how you actually do the problem. I'm not going to go over how you draw the shear diagrams, but I will go over how you get these equations. Okay, so the easiest way to do this, I think, is to always remember that your v of x is just the integral of your distributed load. Now, when you integrate, you normally ignore the constants of integration, but you've probably already learned in strengths, the material, that you need to keep track of. You can't just drop the constants. Indeed, you have to multiply the constants by variables every time you carry them out, or every time you integrate them. So this is going to actually be, this is little w. So v of x is actually equal to capital W plus some constant. Let's call this v naught. This is your reaction. Okay. Now your moment is going to be the integral of your shear. And when you actually do this, you're going to get, and again, that's little v. This is big V plus m naught. So that is the two main things. Now you're going to be like, well, how do you actually do this? Okay, well, let's I'll do the shear for you, and then you can find out how you do the moments yourself. I think once I show you how to do one part of it, it should be relatively straightforward. Let's look at this. Don't forget that you have this point load that's going this way. Whenever I see a point load, I like to, and whenever you see red, you should know that red is important. I only use red because it's like scarring your mind. I never grade with red because it's discouraging enough when you get something wrong, and then to see that it's marked up all in red, it's even more discouraging. But you always want to break this up into x and y components. You're given this value for theta, so this is going to be p. This is p equal omega L, and this is omega. This is going to be p cosine theta. This is going to be p sine theta. You want to find your reactions. Well, if we do sum of forces, right? We have some unknown shear v naught here. We have some unknown moment m naught here. What does v naught have to be? If we do sum of forces in the y direction, we get v naught minus omega L minus omega L sine theta equals 0. So v naught equals omega L minus omega L sine theta. And now we need to so now when we integrate this, what do we do? We said that v of x is just the integral of omega x plus v naught, right? Basically, I'm bringing the constant out here and bringing the constant outside. And what is omega x? Omega x is a constant. Omega x is just omega. So this is just going to be, this is from 0 to L. It's just going to be W x 0 to L plus V naught. And this is going to be WL plus WL minus, let me try to keep this level, minus WL sine theta. And you can check that this is going to be 2 I'm sorry. I messed this up. You're not supposed to put the limits of. You're not supposed to include the limits of integration on this. So this part was mostly correct, but it should just be equals omega x plus WL minus WL sine beta. And if I double check the solution, hopefully this is correct. Actually, if you're looking at this, it will be correct, because if it was incorrect, I would have just started over. Yeah, I'm just gonna. Yeah, this is sorry. Yeah, this is correct. Except I made a small sign error apparently. So the signs here, the signs here are not correct. V equals omega L minus omega X. Plus omega L sine beta. So yeah, so you can work this out. I'll leave the moment part to you. The moment uses the same exact principle. You just need to solve for m naught, and you can find what the moment of due to this load is. You can find what the moment due to this load is, and you want to find what the moment about these loads are around this point. That is part A. Now part B is calculate the centroid of this shape. I don't think I need to go into that on the video. If you need help with that, stop by our office hours, because that actually takes it's a little too tedious to go over on the video. It takes a lot of time to do, and this video is getting a little bit long. For part C, all you have to do is plug in the values. Plug in the values that you got into the equations that you got for A. Oh, and I should note that the equations, the locations of interest here are the min and maximum values. The min and maximum values and locations of the maximum values. So just show that on your diagram. Like you'll have a diagram here. Just point out what the maximum value is, what the value of that, where the maximum value is, and what the value of that is, and where the value of the maximum moment is, and where the value of what the value of that moment is. When you're doing your stress calculations, like I said in the last video, you want to make sure that you include your sigmas. So you don't want to forget your axial load. So your stress, you actually have stresses. You have several different types of stresses. You have bending stress and axial stress. So when you do this, you have sigma due to sigma bending and sigma axial. So don't forget that you have to add these two together. And you also, when you're looking at your shear stress, you have, this is going to be your sigma x. You don't have a sigma y in this case. You only have forces in one direction. You only have normal forces in one direction. And everything else is going to be shear. So your shear, it looks, you're going to use this equation. Tau equals VQ over IT. This moment of inertia you're going to calculate from your centroid. I actually got a slightly different value for the moment of inertia than in the solutions, so I'll be curious to see what you guys get. That's why I'm not giving you guys, not telling you what I got, because I really want to see what other people are getting. But this is the max. This is the shear is not constant, so what you're looking for is the largest. I believe you're just looking for the largest shear value. Let me find the instructions here. Oh, at the location of the maximum bending moment. So wherever your maximum bending moment is, you want to find the shear at that location and use that here. This Q value is, I always mix up Q. Q is the area times the distance to the point that you're looking at. So if we look at here, we're interested in the top of the web. The web stops here. We're interested in this point. So Q is the area of the entire of Q is this area times this distance. Yeah, Q is this area times this distance. And T is just a thickness. So you have all the values that you need there. Finally, part D is just plugging into that equation again from number 2. Part D is just plugging into here. That's all you have to do. Sigma y is going to be 0 in our case because we have no stresses in the y direction. We only have stresses in one direction, so one of them is going to be 0. It doesn't actually matter which one you make 0 because it should all cancel out. You'll get a different sign here, but tan is an odd function, so the sign, how to say this, like, I think you should get the same angle, just reversed, because Moore's circle should be symmetric in it's symmetric in a sense, so the sign should not matter. But yeah, it'll be easier for everyone if you just make sigma y 0. So yeah, let us know if you have any questions on this problem. I think I kind of rushed through some parts of it. So but if you have any questions, just send us an email.